So what is our paradigm that we're operating in? We have lots of disparate data sources, large amounts of overlapping data from different, we have government data that's collected for different applications, a lot of commercial data that's out there, and crowdsourced, or what we call volunteer geographic information, VGI. So OSM is a classic example. When you go out and there's a crowd campaign, you're collecting massive amounts of data. Well, that happens to overlap in a geographic area with another collect. So often we have this scenario where, how do we leverage both data sets to get a best of breed? And that's really where this tool fits in. So conflation, just the basic definition, unifying two or more separate data sets that contain certain characteristics and integrated and all-encompassing results. So you have a source data set, target data set, you merge them into an output. There's a lot that goes on behind that, and I'll get to some of that hopefully, and anything I cannot address, hopefully my colleagues can. What makes it so challenging if it's not immediately apparent? Well, you have different database schemas, you have different data specifications, MGCP, TDS, OSM. Sometimes it's a loose structure, like key value pair associations can kind of expand and grow, and you're basically trying to conflate one data set with another, and they may not, it's like apples to oranges when you're trying to compare tags and values. So how do you do that? Well, that's a challenge. You have it's collected at different resolutions and different geographic scales. Some is collected at 1 to 50K, 1 to 25. In reality, you probably shouldn't be conflating that data. However, there are some scenarios where you can conflate data at different scales, and I'll talk a little bit to that. As well, there's different extraction specifications, how you collect some data. For instance, MGCP is collected specifically at its topographic data. I can't remember what the full acronym stands for, but it's collected at 1 to 50,000 scale in 1 degree by 1 degree cells, and there's a very specific extraction specification for how it's collected, the kind of attribution, et cetera. So we've developed tools to help deal with those sorts of specifications and translate data into a common schema. The tools tend to be limited to desktop solutions, so I don't know how many of you are in the conflation business or have to deal with it regularly. Often, those are thick desktop tool sets out there that you're working on. It's pretty labor intensive. And the manual techniques are very tedious. So what is the Hootenanny conflation suite? Well, Hootenanny in a nutshell is basically non-proprietary, open source technology that supports fully automated and semi-automated conflation of geospatial vector data sets. And for this scenario, we're primarily talking about roads, buildings, and POIs, but it can be anything. It's open source, and we encourage people to participate in this community of conflation that we're trying to create here. So some of the key features are feature matching, emerging logic for geometry and attributes. So if they overlap in, like a building overlaps, two building footprints overlap, and there's a similar tagging structure to those, we basically either merge those automatically or send those to a review, a conflict review queue, which I'll explain in just a bit. There's a flexible value schema, so it can be expanded, it can be scaled as needed. It all lives inside Postgres, and we base it off of the OSM DB. I think it's version 1.5 or whatever the specification is. But so we're mainly talking here about three kinds of conflations: reference conflation, what we call cookie cutter, and horizontal, which is taking two data sets and merging them, but cutting sort of a center core, buffering it, and like merging it into another data set. And then average conflation, averaging the value of either geometry and then mixing tags. It's service-oriented architecture that leverages both OGC, REST, and Node.js, although arguably it's probably in the reverse order of importance: Node, REST, and OGC. Most of our use cases leverage Node services and REST primarily, but WPS is important. We decided to integrate this with Mapbox's ID editor because it had a very flexible framework, and we had a lot of JavaScript developers that can leverage those tools and build it out. So they had already developed OpenStreetMap editor, a very similar framework, and we just simply adapted that to fit the multi-layer approach that we needed. With OSM ID editor, you're primarily dealing with one layer of data. And it supports multiple formats, file geodatabases, shapefiles, OSM, etc. It's also, most importantly, open source, available for download, and you can use it tomorrow or today if you're so motivated. This is just an overview, a diagram of the pairwise conflation workflow. You have two data sets, input A, input B. We extract and translate that data to the Hootenanny key value store, and then it gets conflated by the user through the user interface, and it lives in that. And then any automatic features that are merged basically pass through, and anything that is ambiguous that requires more user input is sent to a conflict resolution queue and for further evaluation by the user. So it is automated in the sense that certain features are merged, and semi-automated and manual in the sense that you interact with certain data that can be confusing to the application. And then finally, the user exports that into whatever their desired output format and translation schema, if it's OSM, MGCP, TDS, or file geodatabase, shapefile, OSM, etc. So it has been peer reviewed. I will not speak to this particular paper, but any softballs can be lobbed to me, and I will catch them. But any hard slider questions, you can go right to my colleague here. He's been working on this project since 2012, and it has evolved tremendously. It started off as basically command line scripts with a lot of code underneath to conflate massive data sets and on a Hadoop cluster, like a country level, 3 countries, and you just send it, and roads, lines, buildings, conflated, done. No user interaction, but that was all that was needed for that particular requirement. And as our user community grew and our needs grew, we had to have a more interactive workflow. And so we're also feeding to other projects with our partners and collaborators on this effort. Where do you get it? Of course, GitHub, where do you get everything? This is just a snapshot of the UI, but I'll show you that in the demo. So I think the easiest way to talk about this is in a sort of data scenario where you would need to possibly conflate multiple source data. For this particular example, I chose to use Samoa, not because I like Samoa, but because there was an event in the past, and there happens to be some very specific data over that area. So for this particular event, there was a cyclone, I think it was a Cat 3. It came through, and it displaced tens of thousands of people, caused $200 million of damage. You could see from this picture that it did a lot of bad stuff to roads and transportation infrastructure. So in this particular scenario, you can imagine that you need to conflate multiple data sources that are coming in so that you can have a gold set you can use for various first response or humanitarian data needs. So you're feeding it back into something like OpenStreetMap or whatever your baseline. So where is Western Samoa? Of course, the geographer in me always needs to know where something is. It's in the middle of the Pacific Ocean, of course, and the capital, Apia. I don't know if I pronounced that correctly, but is a tiny little place that I'm sure has incredible scuba diving, and I would love to go there one day, but for now I'm just going to look at the data. Our data sources for this case, we used OSM, the Overpass API that you're all probably fairly familiar with, and going in and extracting data. So I just did a bounding box extract over Samoa. And another open source data platform, which one of my colleagues actually discovered, the GeoInt New Zealand Data Service, which has MGCP data for mostly all of the Pacific Islands. It does not have Fiji, I discovered, but it does have Samoa and scatter of islands. And it's very comprehensive and lots of data. So it's open, it's available to the public, you just have to register. And it's a good data set to conflate with OSM data because there are similarities, but there are also differences, as you'll see. Also, in addition to this conflation, I wanted to bring in an analyst data set, something that you could collect either through sort of scraping different data sources on the web, or going out and looking for things like, the old-fashioned way, just Googling until you find a data source that seems to match your area of interest. The thing about those analyst data sets is they don't tend to conform to any standard or specification. So we have to do a bit of translation to get them into the system. But that's all fairly easy to deal with. So in this particular use case, our need is to have updated POIs, enriched transportation features, bridges, roads, tunnels, and building footprint polygons. Our available data, OSM, as I mentioned, MGCP, not as dense as OSM, but very accurate. The thing about OSM is it's comprehensive. It tends to be very tag-rich, but the collection method varies from location to location depending on the campaign. And so with standards like MGCP, they have a very specific collection spec, extraction spec, and so you know what you're getting. It's just that sometimes you don't get a lot of meaningful information with the tagging. So I found that it's often good to combine both. And then your analyst data set, as I mentioned earlier. So our two conflation operations that I'm going to do for you guys, conflate first MGCP with OSM data. We're doing in this reference conflation where you take one, and that is the reference data and geometry. You conflate it with the OSM data to fill in the areas that are not covered by that data, as well as merge tags, and then take that result and conflate it with a third data set, which is this analyst. So just kind of a visual on the data. Just highlights OSM has really good coverage in newer, more urban developments. As OSM is the orange line work that you see over there. It's kind of a blurry screenshot. I don't know how to autofocus, but and the green lines are the MGCP. I just loaded this into QGIS for a quick visual comparison, but the MGCP has a ton of POIs. I think there's often a difference in how OSM tends to catalog or model different features. So buildings tend to be polygons, not POIs. So there's a little bit of that going on, but it's still good value to get those features into a single data set. Some just quick tag comparison. We know the OSM highway, it's very extensive. You have different highway types, you have footpaths, et cetera, different surface types. However, MGCP brings in other attributes that are often valuable, like the weather type category. What's the weather that, the weather conditions that allow that road to be traveled. They have lane counts. They have various other attribution that can be quite useful to people during a mapping of natural disasters. So our sort of general process here for ingest is to take these data sources, ingest them into the system, which is translate if they are in a particular schema, or if they're OSM, we just ingest them automatically, and we add a few extra tags. So it's essentially OSM plus some extra tags that are useful for Hootenanny to run its conflation to optimize. We store them in a Hootenanny key value store. And the general workflow here is your two data sets, conflate, merged, add a second. Actually, what should be there is a review step, but I didn't. I'll go through that in the process. So this is just a screenshot of the UI. Here we have two data sets loaded, the OSM data and the MGCP data. This is just, we have a very simple workflow. It's not wizard, it's just locate data set A, locate data set B, what are your conflation options, and go. So we specifically made this as simple as possible so that our customers or end users or whoever that may be could not have a very high barrier of entry to use it. So this is just a quick highlight of after you run a conflation, you can enable statistics so that you can view things like the number of nodes, ways, or relations within that particular data set. You can see how many, you can get a count of how many roads were merged, how many roads went through review, et cetera. Same with points and polygons. This can be useful for evaluating your conflation performance. So we just present that in the user interface so that, well, you can certainly get some metrics out of this. It's not just black box. After you conflate and you resolve your reviews, this is typically what your data set's going to look like. I chose the black background because it highlights the colors a little bit better, but normally it's on top of your usual ID editor base map imagery services. So in this case, the green layer, these are all the automatic merged features. Oh, this really is out of focus, but I'm sorry. The blue, in this case, are input A, and orange are input B. So it kind of gives you a key for what you're looking at. And the stuff that passes through right away, it's always green. So you'll get that after you run a conflation. Is that better? Or that's worse? It's hard to see from an angle. Just what types of features are automatically merged? Well, in this particular example, we have 4 POIs, 2 that are almost right on top of each other and 2 that are nearby. They happen to share very similar names. I think the exact name. One is the German flag memorial. One has the tag historic equals monument. The other historic equals memorial. Because they're geographically close and they have similar tag, then they're automatically merged through. So you don't even have to touch any of that stuff. And the value is that we have people doing this massive conflation, and they're going through tens and thousands of data of points and verifying that they're actually properly merged with all the appropriate tagging. And this automates that and makes life easier for everyone. So that's a case of a automatic review. A manual review would look more like this. You have a similar name. In this case, it's I'll read it for you because it's blurry. Aggie Gray's Hotel and Bungalows. In red, that's the red highlighted POI. In blue, it's an Aggie Gray Hotel. Similar name. They're both POIs. One is tagged with the tourism equals hotel. That's the OSM data. The other one is empty because it doesn't have that tag. It's MGCP data. They don't use that same tag structure. However, Hootenanny recognizes that they're both hotels, that they have a similar name, and they're most likely candidates to be merged. We allow the user to go take that, take the action of merging it in either direction, or just resolving them as separate POIs. So I'll show you that process. And then finally, the last step, which is to export your data into whatever file format and schema is useful to your workflow. Are there any questions before I start the live demo? Yeah? So the question is, what about geometries that are really different, like the example of a building and a road POI? Well, we're not cross-conflating those two. So a road would not conflate with a building, at least not explicitly by the application. There are ways to do things like that, but this is very specifically conflating common features. Like roads are conflated with roads, buildings are conflated with buildings, POIs are conflated with POIs. And they're conflated because they have tagging that identifies them as such. So you just don't have those kinds of scenarios come up. If, in terms of the geometries being different, and there might be a difference of opinion here, but that's where the kind of science comes in, and you'll get the merging. If like in buildings, the more complex building polygon is maintained if you're using reference conflation, whereas the other, and for roads, it's whatever the reference conflation is. In the back. Yeah. So what happens when you conflate two data sets and one has a building and one has a river? Yeah. Right. Yeah. Right. And this data set that I'll have has POIs, buildings, and polygons in it. So, Mm-hmm. Yeah.
One last question.
Sure.
About the accuracy of the system.
Mm-hmm.
So is there a study run to check the accuracy of this conflation? And if yes, what was the process that was followed to do the accuracy assessment?
So that's a presentation in and of itself. What's that?
That is it.
Oh, no. It's not signed up for today, but if you'd like to talk about it afterwards, we can go into details. But we did a lot of comparison between taking humans and having them conflated, quantifying the results of that, and then quantifying the results of the automated conflation and comparing those to each other. And that's a constant process that we go through as we're developing the system.
Okay, so just in this quick demo, I'm going to take you through that workflow that I described in the demonstration here. So we have our two input sources, our MGCP. In this case, I'm going to call that our reference conflation because the New Zealand Data Services might be driving this campaign, and they want to merge all of the OSM features into that layer. So I'll select my layer 1, which is the reference layer, layer 2. The color scheme is simple. We're not trying to mirror what's in OpenStreetMap in terms of symbology. We do some stuff with MapNIC and RenderDB in terms of rendering data. There are challenges in terms of rendering feature layers within this framework, but we're really not trying to present a cartographic map to the user. We're trying to provide you with tools to conflate that data and then export it into whatever application you're using. So here you basically save the name, pick a path, select your type of reference, and whether or not you want to generate statistics, as I showed you in that table earlier. So then the user would just click conflate. Now this will run, and so I'm going to knock out really quick and just show you the finished state, because that's a lot faster. And so, oh, that's not what I wanted. Okay. Technology fail. Well, we won't do full screen. Never mind. But here's what happens at the end after you've gone through the review process. So what you're seeing here is, just minimize this. You're seeing the automatically merged features, the green line work here, so all the roads that it brought in both layers. So the MGCP and OSM both had roads, building, polygons, and POIs. And so it took those two layers and merged what it could, and then those features that there were ambiguous relationships, as I showed you in my PowerPoint slide, those were sent to a review queue. But I'm going to show you that now with this third data set rather than walk you through the review queue of these two data sets, because that's not as interesting. So when the conflation is done, you have the option of exporting that or adding an additional data set. And here I'll just select Add Another Data Set. And I actually have this analyst data set on my desktop here or on my laptop. I haven't loaded it in, so the process of loading is pretty simple. You basically just select your import file type. In this case, it's an OSM file. Open it. We also support geonames, download it from geonames.org. So all of those massive POI files, they're actually pretty small but very rich in data. FIO databases, shapefiles, and I believe that is it, yes, for now. Select your data, you give it a name. Now it's a layer inside Hootenanny, so it's inside the database. You've extracted it. A folder path to basically organize your data virtually. It's more for the user. And then a translation. Now for OSM data, it's not really translated because we just take the key value structure that's there and shove it into Hoot. We already recognize OSM. We're built on that, so it's really easy. If it were MGCP data, we would translate all of the tagging into OSM, convert what that mapping would happen automatically, and everything would be happy. So we just import that data. It's rather quick for this data set. And we go back to our map, add the secondary source here. That's this analyst data. And I put in some features that will hopefully highlight some of these differences. So I'm just going to quickly kick it off here. And obviously, the performance is going to vary depending on the size of the data and what you're looking at, and also the size of the server. So rather than throw out some metrics about like how fast it is or how much data you can conflate, it's really just a scalable application that can serve different needs depending on what kind of hardware you throw at it. So you get a little message saying that the job is completed, but there are reviews to step through, and this is basically what you'll see here. So here you see a review between two POIs, Samoa Polytechnic and Samoa Polytech. They have a similar name. It looks like they're close, but Hootenanny's uncertain as to whether they represent the same POI. So in this case, if you hover over the merge button, you can either merge this MGCP or the conflated data into the analyst data. Actually, the analyst data, the blue, into the conflated data set by just clicking on that, or you can reverse the conflation direction by clicking the control key. So in this case, I'm going to say I think they're the same because they have a very similar name, and then just kind of move through. And we do have hotkeys, so it's not just clicking buttons. I could do this like by typing certain keys and make this fast. In this example, we have one school. It's called Samoa Polytechnic. The other one's called Samoa College. And let's say I'm an analyst working on the system, and I'm doing this review work because sometimes when you get, let's say, tens of thousands of points, you might get 2,000 reviews, which seems like a lot. However, in the grand scheme of things, it does reduce a lot of the manual labor associated with matching and conflation. So I can go ahead and create what I call a bookmark review and say, is this the same test, my email? And so another user can come in and see this. I'm not going to fill this out completely, but we'll get to that at the very end here. So that's just bookmarked for later, so that maybe if I do some research, I can come back and load it, or another analyst can come in and review that. So I'm not going to take any action on that particular review. In this case, we do support one-to-many. So if you click on these POIs, you can actually see the relationships with other POIs that they are reviewed against, and you can click on each and say, okay, well, each review has different tagging. Do I want to merge these all into the single POI? In this case, it looks like it's, if I select this, it looks like it's also, not only does it represent the college, but it also is an entrance. You can't see that there. It has entrance equals yes. So that probably doesn't represent the same feature. But I can go ahead and merge this one here and say these are features that represent the same thing. They're both buildings. They're both part of the college, et cetera. So you work through this. I'll just kind of skip most of these until I get to another example. For buildings, it's a similar scenario. However, you don't merge these two features. You're just reviewing them to see whether or not they represent what they say they do. So in this case, it looks like there is a typo. You can go in and click on the attribution, the tags, and just edit the values and say, OK, it's obviously a typo. So we save that into the local Hootenanny database, and then when you're done, you'll push it out. So that's basically the process of going through buildings. In this case, I just loaded a bogus building to show you that Hootenanny recognized that these were overlapping, obviously. They were right on top of each other. They had similar names. They don't seem to match geometry-wise. So, user, what am I supposed to do with this? And so in this particular case, you do need data stewards that are familiar with the data so that they can take action. And I can just go ahead and delete that. So it's like an editing tool as well. So you can basically just go through this. I want to hopefully get to the road review. In this case, so you can see these roads overlap, but one was offset by a certain distance. And in this case, it's not, Hootenanny wouldn't go and merge these two roads because they are offset. However, they're close enough in their distance, the search radius, that they would get thrown into a review for the users to evaluate. And we can do things like toggle between the conflated layer, the input sources, and the conflated data. These are all hotkeys, but I'm showing you the buttons so you can see. If you're familiar with ID Editor, a lot of it's going to be very similar. In this case, this looks like a bad road, and I do not want that in my output data. So I'm just going to clean it up a little bit. So just move through this process. Again, similar school names. One's called Saint. One's spelled ST. We're just trying to automate this workflow to make it faster for you to conflate your data. If I get to one more interesting review, okay. In this particular scenario, we have what looks like a traffic circle. So what I like to do is flip back between, this is actually really useful to flip back between the input data view and the conflated data. The input data view, you see all of this road work that overlaps, but it's sort of like a mishmash of different lines, and you can really see how Hootenanny kind of dealt with that and kind of lining it up so that it's sort of single road line, what looks to be centered in the imagery. For this particular traffic circle, more action needs to be taken because the actual geometry doesn't match the roundabout, but we can fix that manually by going in and editing the data. So I just wanted to show you the before and after so you can see what's going on behind the scenes. So once I resolve all of these, I can just say, like, okay, I don't want to look at it anymore. I trust what it's doing. And then your option of exporting to your target schema. We do on the other side, actually, so then you select what data format you want it in and what your target schema is going to be. You can manage this all from like an admin console here with the same tools and functionality, but more of an administration workflow. And I think I'm running close to out of time, so I'll take some quick questions if there are any. Well, we like to keep the review conflict workflow within Hootenanny. We do maintain the tags, but once they're exported, I think we strip the tags, the review tags.
It depends on the export.
Yeah.
So you can export it to raw OS. Pulling that into Ingest, you may lose some of that, but certainly
you can go through that process. The problem is that, well, you won't leverage any of the Hootenanny intelligence for resolving those reviews. So we're trying to build in that. Now, something I often do is take it into JOSM and do like post cleanup and just evaluate how that conflation was. But I like to do the reviews in a tool like this because it's generally faster. It queues them up. We have some intelligence for doing geographically proximal reviews. So it's just hopefully an easier workflow. Any?
Your example of the roads didn't get conflated because they were outside the scale tolerance.
Right.
Can you manage those kind of tolerances, and how can Hootenanny serve a conflation situation from a small scale data set, let's say, that might have attribution information to a very large scale, let's say a hydro conflation problem? Can you manage that kind of conflation with Hootenanny?
Yeah, and I'm just going to add another data set so I can show you some of those advanced parameters. You can tune, well, from command line, you can do anything you want, essentially, through passing arguments. And that's how, it's how powerful it is. But through the user interface, we have kind of a select number of options that we're presenting to the users so as not to overcomplicate the workflow in the end. But the goal is to provide you with flexibility so that you can define some of those search radiuses that meet certain unique feature type constraints. Now, in this case, I can expand this to include some cleaning options. You mentioned the search radius. I just want to find it here under roads. So the default value, I think, is 15 meters, or depends on the.
So by default, it reads on a per feature basis.
Right.
So if you specify that on a per feature basis, based on the scale, we have different features have different circle errors associated with them.
Yeah.
And then you can override that here so that it meets the global previous.
But we wouldn't want to use the global if we had a mixture of features that we didn't want to apply that to, like points, lines, and polys. If you have them all in one layer, you don't necessarily want to do that within the same layer. But you might break up your data into those specific feature types and then run and set, say, I want to do a 50-meter search radius so that I can merge roads that are farther apart if necessary. There are other options for rubber sheeting as well that have, so if the data sets overlap enough, you can apply rubber sheets and just, brute force get the match that is more desirable. Any other questions? Yeah.
Would this resolve topological errors between adjacent polygons?
Would it resolve topological errors? Yeah. Yeah. So we're mainly, like as Jason said, we're focusing on buildings, but the project is growing, and if you, it's on GitHub, it's free and available to use, and we encourage people to go and fork off that repo and then, hopefully develop. All of the dependencies are open source libraries. We've taken radical steps to improve the installation process. I think by default it installs in a Vagrant container, but we have installed on Amazon and other environments. Probably, we can try Docker as well. But we're just trying to get in the hands of as many people as possible so that we can expand some of this capability into, fringe cases. If that's it, thank you very much.